Hi, so Aaron, can you guys hear me? Well, cool. All right. So I'm Bruce. I'm from JC's lab, and today I'm going to talk about optimization, specifically for a LiDAR camera calibration. That's a means to utilize different types of sensors. So the goal is to overlay the points. So the green points you are seeing here is the LiDAR points, and you can see the images, and we want to overlay them so that we can utilize the advantage of different sensors. For example, on the right, you can see that this curve aligns well on the curve here. So it's a good alignment. On the left, it's not so good as alignment. So that's just the purpose that we want to do at a high-level idea. And you might have questions that, why do we want to do that? Because we want to utilize different advantage of sensors. For example, for images, you can know that these are grass. They have a color. You know this is sidewalk, and this is sidewalk or pathway, so you can walk. And on the side, you know this is grass, this is tree, this is wall, etc. So you have semantic meaning of the images. And then for point cloud, it's just points, right? You just measure distances. So you don't really have the information of semantic meaning or what the points are. So by projecting the points back to the image and label the points with the label in the image, then you are able to build a 3D semantic point cloud. So that's the purpose of that. And you might ask, what's the benefit of it? So you can see that so there are several types of sensors that, for example, this camera is actually a RGBD camera, which means that it doesn't really give you the RGBD, but also give you the point cloud. And we directly have that already. Why do we need to use LiDAR? Because LiDAR gives you a crisp, clean measurement like this. And then for this, you can see it's really noisy if you just use RGBD camera. So that's the reason. And another benefit of it is RGBD gives you noisy but dense point cloud. So you can see that here's a really thick wall. On the other hand, here's pretty thin. So that's another benefit of using LiDAR, fused LiDAR along with camera, and not just use a RGBD camera. So that's the reason why we want to do this project. So what exactly the problem, and how do we formulate it? So what we wanted to do is we want to find a transformation that can project the LiDAR points back into the camera frame. And so how we represent that is a rigid body transformation, which is a rotation matrix and a translation vector, which you guys have used in, I think you guys call it homogeneous transformation, and you guys use it in project 1. So that's the same thing. And because now we have two frames, right? We have LiDAR frames. We have a LiDAR frame. We have a camera frame. So we use it, the sub L as a from which sensor to what sensor. So that's H sub L sub T, sub C, something like that. And what do we need? So we need we need different features from different sensors. For LiDAR, we need LiDAR features treated as X. We need camera features from Y. And what exactly features would be and what they are. So there are just kind of different specific structures that in your environment. For example, you would have edges, right? So this, on the left is the regular images, a regular image. On the right is the edge detection of the image. So you can see that this is a plane. This is a door, so you can see the edges are extracted. This is extracted. So those are just one type of features that we can utilize from the image plane. Now, we can also have another set of features like corners, right? So we can detect corners like this, and we also have the corners on the LiDAR frame. So the features is actually self-defined. You can define whatever feature you want. There are different types of sensors. There are different types of features like orb features or other types of features. You can detect lines, edges, corners, etc. So there are a lot of features you can extract from different sensors. Okay, so we now talk about the 3D LiDAR features, because those are corners, those are vertices on 3D. And we have camera features, which is corners here. Now you might wonder that how exactly we could map from 2D to, how can we map from 3D to 2D? And for now, you would take another classes, like such as computer vision class or whatever, but that's actually a projection map, and we would take that as a black box for now, which you can imagine that given 3D points, you are able to map it to 2D, but you will learn in the future. So to iterate again, our goal is to overlay the points from the LiDAR to the image so that we can utilize the different advantage of different types of sensors. Yeah, and the thing we're trying to, oops.
I'm tired.
Yeah, too tired. Let me just cut it off. All right, things happens. Yeah, so, and to iterate again, we want to estimate is the rotation matrix and the translation vector that made from LiDAR to camera frame. Okay, so that's what we need. And how do we really formulate it? So what we want to do is we want to find a function that minimizes the, well, after we project the points, we minimize the distance of the projected points on the image plane that we want to find a function of this. So mathematically speaking, we want to project the point, and as I said, that we treat that thing as a projection map, which is a pi here. It's a projection map that can project the points in 3D back into the image plane, and that's the projection map pi here. And we have our, once we project it, that's on the image plane already. Now we have the image corner that we want to minimize it. So visually here is, imagine this is the camera corners, right? We have this camera corner treated as y, like this. And we have this yellow-green points. Those are the projected LiDAR vertices on the image plane. And what we want to do is we want to minimize the distance like this. We want to minimize the distance. Imagine we have the association that we know which corner corresponds to which. We want to minimize it. So that's the high-level idea. Then back to our math formulation. Now, this is the yellowish thing that you guys just saw. And this is the red corners on the image plane. And we want to minimize the distance, so we take the norm of this, and we want to minimize it. And because we have, on the image I show, we have 8 corners, so we need to sum them up. So n here corresponding to 2. So we have 8 points. We want to sum it up, and we want to minimize them.
N is the number of targets.
Yes, n is the number of targets. So we have 2 targets, so n is 2. And we want to minimize it. So, and to solve this function, you guys learned gradient descent. So we'll be using this as our solver to solve this minimization problem. And tomorrow, you guys will learn another technique called Bayesian, which is another second-order derivative of this problem. And you will see the power of the Bayesian, where you could achieve much faster result than the gradient, because they're second order.
Yeah, so is it clear? So Bruce is going to try to find a rotation matrix and a translation vector to make the points that are projected from the LiDAR line up as perfectly as possible with the easily identifiable points in the camera image.
Yes.
Okay.
Yep.
So you've got the parameters in the rotation matrix, which is what's a 3x3 matrix, but all 3 of them are not independent because it is a rotation matrix. R transpose R is equal to the identity.
Yep.
Then you have the 3 parameters in the translation vector.
Yep. So any questions so far? No? OK. So we will run live demo now. So first, you need to download the GitHub, download the code from the GitHub site and download the data sets. And just put it under so you'll go to this and then clone it. And everything should be provided. And then you should see there's a Google link that you can download your data set. And just put it like this. So you have your RUP 101 data like here. And you just put everything that inside here. And specifically, we have a use Bayesian or not. You can set it to use 0 stands for gradient and 1 is use Bayesian. So I would just run gradient descent for now. So everything on your textbook will be showing just by running the code.
Doing this in Matlab.
Yes.
Why?
Good question. So you guys have learned a really fashion of programming, Julia, where I'm kind of old-fashioned. I use Matlab. Yeah, but Julia is the way to go because Julia is really efficient in coding. It's really easy to learn. So I think you guys should use that, and that's the future for now. And for me, I also code in C++ because we work everything on the robot. So all of my codes are actually in, if it has to be running on the robot eventually, then everything will be on C++. But for this, specifically for calibration, we just calibrate it once, and we just take that transformation and maybe calibrate it, I don't know, half a year or something like that, where we figure that the projection is not correct. Like you see in the image that it's not correct, then we will do a recalibration. But that transformation, after we fixed, that remains fixed. So that could be done offline, that we don't have to be done online.
Okay, so you've got a number of iterations, 5,745 iterations of gradient descent.
Yes.
It would be hard to do that by hand, I guess, huh?
Try it. Let me know if you finish it.
Okay.
Yes. So it takes 3 seconds and run 5,700-ish iterations. And you can see that everything you show on your textbook I will be showing here, including the result of calibration and the miscalibration and how the vertices are estimated like this. Yeah. So everything here, everything on your textbook will be here. Now, let's try another thing, which is Bayesian. Remember, 3 seconds, 5,700 iterations. All right? Now let's change to Bayesian. Well, it's done. 14 iterations, 0.1 seconds. All right, so everything the same, but it's much, much faster. So that's a powerful technique that you guys will learn tomorrow.
Yeah, so the Hessian is when you use Newton-Raphson applied to the gradient. So the gradient vanishing is the necessary condition for having a minima or a maxima.
Yep.
So extrema. So what you're really looking for is a root of the gradient, because you want the gradient to be 0. That's a root finding problem. Newton-Raphson solves that. Newton-Raphson needs to take the Jacobian of the gradient then, and that gives you the Hessian. So, but it's just a couple of very quick calculations numerically.
Yep. So
and then you're doing Newton-Raphson.
Yes. So if you're interested in that, actually you can dig into the Matlab code. It's pretty trivial, just like the Julia languages. So if you dig into that, you will see that I do not represent your rotation as just 3x3 matrix like this. I represent it as the 3 parameters, omega 1, omega 2, omega 3. Yeah, so those are, I represent them as a Lie group. So that it can keep the property of rotation group, which is R times R transpose should be identity, something like that. And especially the gradient group, so it should be, the determinant should be positive 1. Now, I also have the backup slides for you to look into if you want to know how do we actually project the LiDAR vertices back, 3D LiDAR vertices back into 2D LiDAR vertices. That's the backup slides. And everything is published here and the GitHub for the real data. And welcome to Michigan.
Eva, you want to start getting set up? And we'll let Bruce take a few questions while you're getting set up. So Bruce, thank you very much.
Yep.
So anyway, it's just a practical use of how you use gradient descent, not on a made-up problem like we do in homework, okay? This is getting the 2 sensor things, and you're solving for a rotation matrix, which seems pretty complicated. He did a matrix exponential of a skew symmetric matrix. Math is power. You guys will learn that if you do more robotics and mechanics courses. You'll learn how to go back and forth with that. Can't do everything year 1, right? You got to save something for year 2. And then Mani will go through the Hessian tomorrow in lecture. And you saw the huge difference in performance. And if you're just doing one calibration, who cares? 3 seconds to 0.1 seconds, you just don't care. But on other problems that are much bigger, the factor of 30 speed up, yes, okay. That's the difference between you sitting there bored for hours and getting a result in 5 minutes, okay? And as an engineer, sitting there bored for 5 hours is just ridiculous, okay? Just waste of time. Questions for Bruce?
Oh, can I put a question in the chat? Yeah, so that's a good question. Depends on your knowledge.
Repeat the question because they can't see it.
Okay, so the question is, how do you choose what features are easier to use in different scenarios? So that's a good question. That actually brings the question back to why do we use target-based calibration? There are actually out there, there are actually different works that are used targetless. The reason why we use target-based calibration because we want to calibrate the sensor everywhere, anywhere we want. For example, we can bring the target to the forest, we can calibrate it, but for those targetless calibration, I highly doubt they can do it in a forest.
So what Bruce means is some people can use sides of buildings as a dummy target, okay? But it's hard to use a ton of different tree trunks. It's just not an accurate enough way to pull out features. But these targets are small. If you can schlep a robot and some extra batteries, you can throw the targets in the same wagon and then you can set up and recalibrate if the robot falls, okay? Makes it very easy.
Yep.
Excellent question. Okay, Eva, we're going to turn the floor over to you. Would you like this lowered a little bit?
Yeah, that'd be great.
Is that too much? How's that? Yeah, it should be electric, okay? It's not even fair to make it. Yeah, there's a handle here you squeeze. Yeah, it's mechanical. That's why. Oh, you're a mechanical engineer. Yeah. Yeah, so Eva got her bachelor's in mechanical. She's got her master's in mechanical, and her PhD is in robotics through the mechanical engineering department. Yeah. And Eva, Grant, and Wami wrote the original Project 3, and Eva's here to give you guys enough insight so that you can work the project in about 2 hours.
All right, that's the goal. Can y'all hear me?
I don't set the goals low, Eva, okay?
We'll see if we can achieve it. So yeah, today we'll be talking about Project 3, the Segway project. So how many of y'all have actually opened up the document for the project? It's okay if no one has. That's why we're here. So the outline of the talk will be, first of all, going over model predictive control, because this is sort of what Project 3 gets at, and then going over a quick overview of what Project 3 is, and then a simple problem to sort of help y'all get started on Project 3. Cool. So what is model predictive control? Has anyone heard about model predictive control? I see shakes. I see Bruce raising his hand. All right. Does anyone want to take a guess as to what this is? Big hint, predictive. Yes, go ahead. Yeah, that's actually not a bad guess. So the answer was going back to the diagram that I had back here. You have to derive your model, right? And that can be done using the free body diagram right here, and then from that, try to derive a controller. The thing that I want to emphasize about model predictive control is the term predictive. Now, let's just take a look at some examples where we, as humans, use model predictive control. So for instance, I don't know how many of y'all play chess. I personally do not. Okay, I see a hand right there. So you know when you play chess, right, you sort of have to anticipate what your opponent is going to do, right, before you make your move. And you make your move based off of what you've done in the past, what you think your opponent's going to do in the future, and that's how you make the move, right? All right, let's say that you find yourself in the middle of a puzzle. This is from a Netflix show called Floor is Lava. And you're told, you know what? you have to get from the entrance to the exit, right? And you can see that there's various paths that you can take, right? And so here the question is, what do you do? And so I guess what a person would do, they would sort of look at how all the paths lead, how you can get, for instance, from the yellow path all the way to the exit, and based off of that, then choose your first move, right? Hopefully, you would not choose your first move before sort of planning ahead, but hey. Here's another example. So how many of y'all played tag as kids? I mean, I did. I love tag. All right, turns out that tag is actually, whoops, that played the wrong video first. Let's play this one. So this is actually a competitive sport. It's called World Chase Tag. And the goal here is, as you guess, you have someone who's trying to tag the other person. And I don't know, when y'all were playing tags as kids, you sort of had to sort of, again, predict where you were gonna go, where your opponent is gonna go before you take that move. So that's that one example. It's so much fun, right? Here's another example over here. Let me pause this one. So this is an actual example of a robot, in this case, a drone, using model predictive control to avoid the obstacle, which is the yellow ball. So this is not just some concept that's theoretical. It's actually applied. And we actually applied it, not me personally, but Grant actually applied it on Cassie. So it is out there. So now that we have those examples, whoops. Okay, come on. Question, what is MPC in general? What would you say? Any guesses as to what the answers for these are? So using the information of the what? It's a huge hint.
Class participation.
So again, think about it. Right before you make your chess move, you want to think about what you did in the past, right? Right before you try to evade your partner in tag, you might want to think about, oh snap, I did that move, so now let me make another one. So, any takers? Yes, go ahead. Yes, okay. So let's see how we did. So yeah, exactly. So using the information of the past states, right, and where you are right now, predict what would happen in the future so you can act appropriately now. Does this make sense? We do this on an everyday basis, even walking, right? Cool. So that's what Project 3 will be about. So now just a quick overview. So in Project 3, your goal will you'll be working with this lovely segue over here. And your goal will be to get the segue from whatever position it's in to a specified X position as well as an angle. Now, that seems a little bit complicated, right? Like, how would you even start doing that? And so what Project 3 also does, it actually has you working with this. Y'all can't see my mouse. Where is it? Anyways, it has you working with this simple car on a straight path example. And you do the same thing over here where you take this car from whatever starting position is to its goal. Does that make sense? A little bit? It's gonna make more sense. Any questions about that? I wanted to also pull up the document real quick. But yeah, so like, this is the Project 3 document right here. And so this document is actually very, very informative. And what we'll be doing in class today will actually just be going over some of the concepts covered in the document in a little bit more detail. But if you ever find yourself stuck at any point or place, this would be a good place to start. So yeah, cool. Awesome.
Yeah, there's a really big word in there, differential.
Yeah, we're gonna get into that. All right, so let me paint a scenario for y'all. Imagine this. You landed your dream job at a self-driving car company, right? So yes, I saw some nods and some excitement, yes. However, your first job as an intern, they tell you, hey, we have this simple self-driving car over here. and we're trying to get this car from point A to point B. Your task as the intern is to write a controller that will get that car to achieve its objective. How do you do that? Where do you even start? I mean, y'all already have the knowledge that you need to actually do this problem. And so that's what we're actually going to take a look at. So this is the outline of what we'll be doing today, as well as in the next lab. So the first thing we'll do is talk about how to derive the dynamics of the equation of the car. For some of y'all who were in recitation, I think 2 recitations ago, there was an equation of motion that I told you not to worry about. We'll work on this. Today is the day that we actually derive that. We'll then go on to talk about what's the relationship between a trajectory and a control input. Again, those are a bunch of random words right now, but hopefully they'll make sense once we get there. And then lastly, we'll get to this cool thing called a state transition matrix. Any questions so far? Awesome. So what are the learning objectives? This is a lot, right? And so today, the first thing is, hopefully to learn how to derive the equations of motions of simple systems. And number 2, understanding how the control input affects the system's trajectory. And that's what we will do today. Awesome. So there is a Project 3 lab assignment that was released. Have y'all been able to access that? Great. So that's where we'll start. So let me see if I can pull it up. But yeah, so the rest of the section will just be y'all working through that document and me coming through for if y'all have any questions or whatnot. So yeah. Let's see if I can pull it up. I do not have it yet. But yeah, it looks like this. So the first thing that we do is we go over describing the motion or dynamics of the car. So the document goes over how you derive the equation for velocity. And your first question is, how can you do that for a position? So just read through the document itself and see if you can do that, as well as go through the other exercises. Are there any other questions? Has everybody been able to open the document? Awesome, awesome. I see some thumbs up. Great. All right, hopefully this is what we were able to get. Were we all able to at least arrive at this solution? Yeah, I see nods. If there's any confusion, I will come and explain it. Okay. For the next part, here's a hint. Using this, see if you can pull out the A and the B matrices.
So, if you look at the equations on there, your position is going to change your position velocity delta line. And your velocity changes with velocity versus acceleration.
Right.
For the people on Zoom, this is what PK plus 1 was equal to.
So you're going to need some component of that gets you B. You're going to need some component of B that gets you that K over time.
That's fair. It's
So you carry position.
It's not the
There of
time to use the column times row string, okay? That's revealing the onion.
Hopefully this helps out a little bit more. Just a reminder of matrix multiplication.
Okay, what's this entry? What's multiplying pk and that vector up there? Uno, 1. Okay. What's this entry? What's multiplying vk in the first row? Delta t. Yay! Now we go to the second row with vk plus 1. What multiplies pk? 0. Okay. Now, second row, what multiplies vk? Uno. Okay. That's how you get the A matrix. That's how you get the A matrix. Now, do the same for B.
What dimensionality is our position?
There was no has to be too many. I literally showed you when he read. I had nothing.
Does that make sense? Yeah. Let's run through this real quick, okay? Let's actually derive the equations right now. All right, so this is what we have, right? And we are trying to derive a matrix A that's multiplied by xk plus a vector B that's multiplied by uk. So the question is, how do we do that, right? So let's take a look at the first equation here. We have pk plus vk multiplied by, I'm going to call this dt. Okay? So matrix multiplication. If I want, so we just have to focus on this part right now because the first part of the equation doesn't have anything to do with UK, right? So put a 0 there. We don't need UK. All right, from this first equation over here, what can I multiply with PK, right? Remember, matrix multiplication, we go row multiplied by columns. So what can I multiply by PK here to give me PK? 1, exactly. All right, so that gives me PK, right? And we know that, again, I'm just going to write A, B, C, D, E, F, right? So I go A times E plus B times F, right? Okay, question. What can I multiply by with VK to give me this? DT, yeah, exactly, thank you, DT. All right, now you do the same thing for the second row. You take a look at this equation, you ask yourself, does it depend on any of these variables here? If so, what do I need to do? What do I need to multiply it with so that I can get what's on this side? And does it depend on UK? So from this, we can do the same thing. So I heard a 0. Where's the 0 going? Row 2, column 1. Yes. Yes, thank you, on the chat. So what then goes here? What do I need to multiply? How does VK appear in my second equation, in the second row? It appears once, so it's just by itself. So this is just a 1, right? Great. So then how does my UK appear? Exactly, so it's dt over m. And guess what? That's what your A and your B matrices are. That's how you get your equations of motion. So it's a lot of matrix manipulation. So any questions on that? Does this make sense? I see thumbs up. Hopefully from the chat it makes sense to you over Zoom. Yeah? Great. Awesome. I know we're over time, but we're going to go into recitation time as well. Awesome. So then the next part, so then we can move on to the next part of the problem. So the question now is, we have an equation that looks like this. Right? And this equation tells me that from a certain position, xk, at time k, if you give me a position at time k and some force, I can tell you where you will be at time k plus 1, right? So the question now is, how exactly does this force impact where you'll be? You know, how do these variables interact with each other? What does it mean that we have this A matrix? So that's what part 2 is about. It's about the relationship. It's about how this equation performs. So part 2 is just a bunch of problems just to try and get you to, to at least think about the equations that we just derived. Okay, so just to go over what the problem is actually asking for. So we derive our matrices here, right? And we know we have this equation here, which is xk plus 1, which is equal to pk plus 1, is equal to our A matrix, plus our B matrix, right? So what these problems in problem 2 are asking is, can you find me a UK such that, starting from whatever position you're given here, so for a particular problem, this is actually P0, V0, right? And I'll actually just write it down. So for ours, we are trying to 5 and 0. dt is 0.1, and we're trying to go to 8, and v can be anything. Can you find a UK such that you can get me from 5 meters to 8 meters? I don't care how fast the car is going, but can you do that in one step? So what you can start doing here, oops, come on. So what you can start doing here is you can start writing down your equations, right? Start writing it down in terms of the velocities, or whatever it is. These are multiplications. The answer would be what? No. Okay. Who said that? I wasn't looking up. Hold at that. Hold at that. Let's give your classmates a little bit of time to think about it. If you know it, go ahead and proceed to the other parts. And once you get this, the problem 2.2 is done in the same exact way. So just, again, write down the equations and see where the force is coming in. So let's talk about 2.1 now, right? So the question is it possible to find UK such that you can go from 5 meters to 8 meters? And the answer is no. And the reason for that is if you take a look at where your input is affecting your equation, It's coming in at the velocity level. So that means if I'm starting from 0 velocity, it doesn't matter what force you give me. Within one time step, I won't go anywhere. And that's because of the dynamics I have, right? So I could have had other dynamics that maybe had dt over here. And yeah, in that case, maybe I could have found a UK that would have taken me to 8 meters. So the reason here is that because of our particular dynamics, our input is coming in at the velocity level, which means if you start from rest, you need more time steps to get to what you need to get to where you need to go. Does that make sense? I see nods. Does that make sense in Zoom? Just hit me with yeses or nos. Yes, awesome. Thank you, Luke. Great, okay. So the answer was no. Oh, let me go back to the laptop. Nope, it's a laptop one. Yeah, so the answer was no. And you can sort of play around with the simulation and try out various kinds of inputs and see if it'll take you anywhere, but they will not have. So, I almost gave you all the answer. I hope you didn't see that. Now we can try the next question. Feel free to use the animations to help you out, but think about it in the same exact way that we thought about it in problem 2.1. Is it possible or not?
You're welcome.
I was wondering, it's been a while since I've that many things.
You recognize it, so that's
Of course I recognize it. It's that many things, so that's good. You don't recognize that many things, so we're
I at least second.
So did everybody get the solution? I see nods. Yes, yes, perfect. Whoops, let me switch back to the actual thing. And Luke in the Zoom chat got it a while ago. But it's negative 120. Do we have any questions on that, on why that's the case? Okay, great. Can move on to the very last problem of today. So let me talk about this really quickly, just to make sure that we're all on the same page. So all we're saying here is that given x0, so if x0 is given, I can find what my x1 is if you've told me what u0 is, right? This is just from the equations that we were dealing with, right? Same thing. If I know what x1 is and what u1 is, I can give you x2. But get this. We know that x1 is equal to a times x0 plus b u0. So why not just plug that in? Right? And I end up with this equation. And I can do this over and over and over again up until xn, and I end up with something like this. Right? So all this is doing is you just x1, write what it is. When you solve for x2, ever that x1 pops up, you plug in ax0 plus bu0. I see some nods, so hopefully this is making sense. So then the question is, let me see. Here, given an initial position, 0 meters, 25 meters per second over here, and a constant input u, which means u0 is equal to 3, u1 is equal to 3, u2, so on and so forth, can you tell me what x0 is, x1, x2, x3? That is what the question is asking you, using those equations over there.
I think it's
Perfect. Okay. So really quickly, show you all what the answer is. This is how, if you're using a pen and paper, this is how you should have been solving for this problem right here. And let me just show them the code. But I did mine in a for loop. This is how I did mine. And that's the answer right there. So you could have done this in a lot of different ways. You can either do it in a for loop or just write every single thing, you know, in each line. But this is just one particular way to do it. Awesome, great. You know, let Trivy set up now.
So for what's new this week, it's a project, it's homework 8. And I think homework 8 is all about proof finding. You're doing bisection, modified bisection, Newton's algorithm, Newton-Raphson. I have examples for all of these up, and I'll post the answers online. But in case anyone's tried the homework in this, or in class, if one of these things was just unclear, we can take that up now instead of going over the whole notebook. Has anyone tried the homework yet?
Go.
Yeah?
Thursday?
Sorry?
Homework on Thursday?
Homework 8, yep. Yeah, you're good with it? Any part that was a little bit hard? No? Yes?
What?
Any part of the homework you're struggling with, or Newton-Raphson or Newton's?
Maybe, could we go over constructing Jacobians? Could we go over
So what's the size of your
The what?
Jacobians?
The Jacobians? Yeah.
It's going to be 1 by 1.
Right. So,
Is this not correct?
So I think I have Jacobians in this Newton-Raphson's example. If you can go over that, maybe that would make more sense. So in class we talked about Newton-Raphson, which is just doing the Newton's algorithm with a vectorized function, right? So instead of having a function like this, and me telling you, find the roots of this function, you can clearly tell it's -1, but what you're going to do in the Newton's algorithm is say, you're going to go from -3 to 3, and then you're going to look for roots in between, and you follow the slope, right? But your function is just this y in terms of x. There's an f of x, which is a value, which is your single number, a scalar value x, right? But what happens when we have functions that are vectorized? So my function f of x returns a matrix where each element of my matrix slash vector is a function, right? There's 3 functions essentially. And I want to find roots such that, like a value of x such that all these 3 functions converge to 0. So that would be the root of all these 3 functions, right? So with that logic, we define a gradient. So we have del f by del x, which is the gradient, in the Newton's method. In Newton-Raphson's method, where your function is a vector of 3 different functions, your gradient essentially becomes a Jacobian. Now, it would be a better example if I had more variables in it, but I have like a smaller-ish example that we can go through. So your Jacobian is basically just the differential of your the Jacobian is just a matrix of differentials, a matrix of partial differentials. And we're going to see how we can do it. Squared plus y plus z, and this is z squared. F of what would be the Jacobian of this matrix F? Do you remember? Yeah.
2x 0, 0, and then 1, 1, 0.
Right, I'm assuming the first element is x, y, and the z.
Oh.
So this should be 1, right? This term is del f1 by del x.
I was working like column.
Right, no, you gave me the transpose. Then this should be 0, 1, 1.
Oh, that's a
Z is 1.
Oh,
Sorry.
yeah.
And
Then
then-
0, 0, 2z, right?
Yep. So that is your Jacobian, which is this matrix a function or is it a scalar matrix? This is still a function, right? Because it's going to take a value x and a value z at least. Right? So my Jacobian is a function of, again, x, y, z. If I want to make that a vector, let's say capital X, so then it's a function of capital X. Okay? So that is your Jacobian. How do we use our Jacobian? Well, if you remember, for Newton's method, when we just had one function, my f of x was x squared, then my del f of del x was 2 times x, then I could say that my xk plus 1 is xk plus del f by del x, some step time, sigma times f of x k. Right? That was Newton's method. Now Newton-Raphson is just the vectorization of that, right? So instead of my derivative, I'll have the Jacobian. It's the inverse of this, right? Do you remember? Divided by del f by del x.
Can you read what the...
Like here. Sorry?
Can you do that up on screen for this?
This thing or the other thing?
That.
This one? Okay. Yeah? which is what we wrote down in the other app, right? Xk plus 1 is xk plus delta plus sigma times inverse of this times f of xk. Then the vectorized form of this, I make the gradient to be the Jacobian. Okay, so then this becomes the inverse of the Jacobian. This becomes the vectorized function f at some xk. Step size, this is xk plus 1. Right? So this will be, this part is newtons, and this is Newton-Raphson. Does that make sense? Yeah.
What's that symbol next to inverse?
Oh, that's the step size. So I put an epsilon. Can be anything.
Can you repeat that?
Step size, like damping ratio.
Yeah.
So
And
do you
that's
remember?
epsilon?
Yeah, epsilon.
Okay.
So basically, when we were studying Newton's method, do you remember without the damping, we ended up saying that this inverse, the derivative sometimes can be really small, which can blow up how much we add. And that means we end up taking very large steps against on the line of the derivative, right? So what we end up doing is we multiply it with a very small constant, usually like 0.01, to control that derivative that we're getting. Does that help? Is it easy to see how the Newton-Raphson is the same as Newton's, but it's just vectorized? Like if you try to do it for x, y, and z separately, that's what the equation is coming out to be, but it's just contained in a vector this time. Does that make sense? Kind of, sort of? So I'm saying that these two are comparable, because when I open this up, it's going to give you, it's not exactly the same, because your variables are somewhat dependent and you're trying to get all of them to condense. So if there's relation between x and y, that will show up around in your Jacobian. But essentially, for a vectorized element, your derivative is your Jacobian. Yeah? Making sense? Right. So, when you try to do Newton-Raphson, so I give you a function f, then the backward step if you want to use QR. But let's try to do one step of Newton-Raphson. So what will your delta be? Remember, delta is this term right here. Delta xk. From that equation, delta is simply, well, you should be doing QR and LU and not take the inverse of this Jacobian right here. But if we were to take the inverse of the Jacobian, your delta is just inverse of the Jacobian times f of negative sign. Does that make sense? So let's see what this would look like. So I give you a function, a step size h for calculating the gradient. Then I give you a function that can calculate the Jacobian. I also have an analytical Jacobian where you can just differentiate your variables, and that gives you the function. And I should be using linear algebra. So let's run that. Right? So that is how much you need to move from your x0. Right? Yeah.
I was just, so when we're going through it, it doesn't seem like we're, or I didn't see if you were using the epsilon route. Are we supposed to use that, even like also like on the homework too, when calculating the Jacobian, or also when doing like Newton's method too? Like, should we be accounting for the epsilon, or that's kind of an optional thing that like makes it more accurate?
Right. So for the Jacobian, you don't really need the epsilon, right? Only for the methods where you have an x and you're moving in some direction, you need like an epsilon when you're dividing by the gradient.
Okay.
But you should be using it because in most cases, your step size, like your delta, right now if you see, it's really big, right?
Yeah.
I have x0, which is like 1, 1, 1, right? And my delta is like, it's too big.
Yeah.
It's very confident in its direction of gradient. So it should be confident, but it shouldn't be this confident.
Yeah.
So you need to make it, I'm going to use like an epsilon of 0.01.
Okay.
Because I look at these values and I'm like, I was in 1, 1, 1, right? So I want to have all these around that value.
Yeah.
You shouldn't be taking really big step sizes.
Okay.
So you should look at your delta and decide what your epsilon should be
Gotcha.
for what it would make sense for the scale of your problem. So my x1 in this case would be x0 plus epsilon is 0.01 times delta. And then these values make more sense. So I started from 1, 1, 1, which was my initial guess for the minima, right? I thought my first guess for the root of my function was 1, 1, 1. Then I took the gradient and I revised my guess. And now my next guess is 1.2, 0.5 minus 0.47, which is more within the range. It's not drastic, right? Which is why we need the 0.01 multiplication. So once we know how to do like one iteration of this, can we do nth iteration of this where, so ideally you should just use like a while loop and stop when you find a solution, but what I'm doing is I'm in a for loop. I look at my f of x. If my f of x vector is almost equal to the 0 vector with a tolerance of 0.01, I stop my for loop with the break statement and I assign my solution to whatever value of x I'm at, right? But for when I haven't found the solution, I need to be iterating exactly like we did here, right? So I'm going to find the delta, x, right? I will calculate the Jacobian for all of my x's. And then finally, at each iteration, I'm going to update my x. And that should give me the new solution every time. And I keep looking for f of x for my e. for every time I update my x. I keep looking for the new f of x, and I try to see if it's come down to 0. If it's come down to 0, I found the root, I can stop, exit the loop, return the solution. If it hasn't, keep going down the gradient. Right? When I run this in 8 iterations, I get my f of x around, this is almost 0, the second element is down about 0, and then the third element is also 0. So I was able to find a loop in 8 iterations. Is this making sense? We're using the Jacobian, we're using vectorized functions, we're going down the gradient, finding roots of nonlinear systems. Yeah? Right. I think most of the homework is just, I would say, look at the pseudocode, it's going to tell you everything, and then just try to implement it, and it should be pretty easy. So, which is why we thought, like, you guys could probably handle the homework without the labs, because this homework is somewhat, you just look at the pseudocode and you implement it. Good? I'll stop here.